how you guys doing today? You doing good? Perfect. All right, so we'll move on to the next topic in chapter 17. So we're gonna learn about the reactions of alcohol now. All right, so if you look at if you try to recall what we learned in over 1, we had some maybe I can do it more like this one. If you have a tertiary alcohol, you can treat it with some strong binary acid like hydrobromic acid and chloric acid over here. Okay, so if you do this one over here, what happens to this one is you're gonna have a lot of protons in your solution there. So this will grab this oxygen in the hydrogen group will grab this one. So become looks like this. Okay, and then obviously either in this two scenario, maybe we can do this one to just. So we have this one came on, and bromine anion is over there, and then as you can see, this is really good leaving groups. This is really good leaving groups. So we'll leave. This is a positive charge, so this will take this over there. Okay, so this will become water and left. Okay, so after this, then you're going to have carbocation with a plus charge on it because water just left now. And then you can have the bromines coming in. So it goes same thing with the HCl, chloric acid, hydrochloric acid here. Either this carbocation form, the chloro groups can now bond to there. Okay. So you can say so this is a way we can get the SN1 reaction we learned before to make the alcohol to be alkyl halide. Just doing this. So obviously this is much easier with the tertiary because it would guarantee your carbocation form will be much more stable that way. Okay, so this is kind of a good way to making alkyl halide from the tertiary, very highly substitute carbon, the hydroxy group alcohol, tertiary alcohol to be that one. Okay. All right. So how about we have a secondary, okay? Or primary or secondary alcohol? What we can do about this one, okay? So if we have, for example, some type of a secondary alcohol, as we can see, it will be better if we can use SN2, not 1, okay? So this will be only attacking from the back side, meaning if it's less bulky, where you have the carbon that you're going to attach your groups, it's better for them to be replacing. So if you do this one, you can do two-way. Okay. You can use the dionyl chloride, or you can use the phosphorus tribromide over here. Okay. So this is the. Okay, let's do this one first. Over here, and then what happens to this one here is they're going to take this one over here, and then this will leave. Okay? And then once this is positively charged, this will be leave. This will leave. Okay. So eventually, form this one, okay? And then this chloro group can now going to be the back side, okay? Back side. So it goes to the here, and then once it hit it, so it's happening at the same time. Now it leaves there. Okay. So you can have a inversion of what the stereochemistry, because the once you have the hydrox group on the right side, in this point of view, your chlorine goes on to the back. Okay. This is obviously yeah. So eventually you're going to have this one as it leaves to there. But the point here is it has happening on the SN2, this inversion, because it's secondary, not tertiary, so you can do SN1. Okay. Does it make sense? Kind of. All right. So another way you can do it is you can try to do PBr3 phosphorus tribromide here. So it's pretty much the same here. They're going to grab this one, okay, and then this hydrogen also leave at the same leaves too. So it gives the this one. Okay, so. Then it'll leave here, and then this will goes to here, this so forth. Okay. So in this case, this will also going to attack on the back. So in here, you're actually going to have inversion of stereochemistry, which is also SN2. Okay. We did it because the this is like a primary or secondary, so we want to use it as SN2, which will have addition of the groups, new groups bonding to the back side. So it will be inversion of the stereochemistry. So this is a quick review. Okay. But then there's a special groups you can use is what we call para-toluene sulfonyl chloride. Okay. So this is what it looks like. Okay. Sorry. So yeah, you're just gonna do the same thing. So if you have a hydrox group on your R group, which is your alcohol compound, right? This will just switch to this one. Okay. So that goes to this one, and then this group we can just abbreviate like a tosyl chloride groups, or you can say OT OS. Okay. This is okay, so you can form this one. So sometimes we use this one because this you can do some lots of stuffs for the turning your compounds into the alcoholic. So I can show you one example here. So remember this one. Remember this one. Okay. So I'll give you one example here. That is the. Okay, that looks like. So we have. Hydrox group in here. I'll show you the same thing at the bottom. Okay. And then if you treat it with the phosphorus tribromide over here, this is SN2, right? Like I said. So this will be showing you inversion. So your bromo groups actually attached to the front, because your hydroxy group is on the back. Because this is SN2, your new group will attach on the front side over here. Okay. And then you can treat it with the sodium ethoxide here. This is 2 carbons with 2 hydrogen, 3 hydrogen with this oxygen. So it's like an alcohol, but it's more hydroxide ion form. So it's a sodium ethoxide over here. If you treat with this one over here, this is also SN2. So we'll actually, this will attack on the back again. So this will actually become So the thing is, you have alkyl groups, alkyl compound that has a hydroxy group on the back, but it goes over 2 times SN2. So eventually, you can have this ether group on this compound on the position you had for hydroxy group. Do you see? So this is on the back here. Now you have a ether group bound to your compounds on the back as well. Because it goes back and back, it should be the same position. But sometimes you can use the paratoluene sulfuric chloride here is when you do this one, okay, when you do this one, you're actually going to have, so this group will attach to like this, right? Because you don't change any position. They only lose the proton there, but they bound to the torside group over there. So they were going to be no change in the position here. So if you treat with the same sodium ethoxide over here, which is SN2, you're actually going to have an inversion of the position. So this is going to be actually on the front. So this is why sometimes you want to do this one because you may want to change the position of your the groups that attach to your compounds. So you can actually either choose this one or this one to make the right stereochemical compounds you want to make. You want to do some practice on this one? Okay, let's do this one. Okay. How about we try to do maybe, can you guys try this one real quick? Maybe I'll show you. It's better. It takes about 1 or 2 minutes, but we'll do this together. about 1 minute. Just try to think about the position, okay? What the stereochemistry it can differentiate from to each other. Okay, so okay, once again, this is going to be SN2, SN2 twice. So you're going to have your groups are attached to the front side because you actually adding the hydroxide on the same side you had for the hydroxide. So hydroxide groups. So it'll be inversion. So it'll be bromo on the back, but they're attached on the front. So it will be here. So you can say this one. Okay. For this one, you can say what you have. You're going to have this group just change to positive group here, and then you're gonna do the inversion of that one by doing this one, which gets into here. So actually, they're coming onto the back. So on the back, then they're going to be on this side. Okay. See the difference, right? Okay. Good job. All right. So the move on to the next one, which is the now we're gonna do elimination. Okay? We're gonna do dehydration. So this one you can try to do. This also tertiary alcohol. Okay? You can treat with some acidic conditions. Okay. And just a little bit of heat. Okay, that might be good better. And then what it happens to here is this. If you look at the hydrogen cation over here, they can break apart as the hydrogen cation, proton, and then water. Okay? So obviously the oxygen here in this one, yet there's still very poor leaving group. So it can leave right now, but it bound to maybe one of the, because now you have lots of the protons there. So we'll grab this one over there. So it will become water. As you can see, this one now much better leaving groups, so you can leave. So they try to leave by taking these two electrons in here, so they become water. Okay. But obviously that makes what? This position positively charged, because now it lost the electron to the water. Okay. So then you see this is water here, also can coming in, and then try to grab the hydrogen on here. Okay. Try to grab the hydrogen here. And then this pair of electron were previously in the carbon and hydrogen goes to there. Okay, so then this one. Okay, so this is elimination E1. Okay. The okay. So can you guys probably try this one? I'll give you about 1 or 2 minutes. So I'll give you another tertiary alcohol here. Okay. Maybe 1 or 2 minutes. Okay. And you gotta try this one. Little bit of heat, little bit of heat. Yeah, we'll do this together. Don't worry about it. Just the yeah. Okay, maybe 1 minute. Do this together. Okay, 30 seconds. try this first, okay, and compare that to the answer. All right, so the if you have this one over here, obviously you're going to have this one because you're going to remove this one as a water when you pick up the protons, and there goes the positive charge. The hydrogen will be picked up by the water, okay, so they become hydrogen cation. And it goes to there, so it will be double one. Okay, so the answer is this one. But the thing is, you can also think about the water can pick up the hydrogen here and here this position too. Then that would make this one. But whenever you do this one, this will become major products, and this will become minor, following Zaitsev rule, which means whenever you have two possible forms, this will become major because it has more substitute in this double bond. This is only two, there are three, tri-substitute, di-substitute. So among these two possible products, this will become major because of the highest solubility on this double bond. Okay. But this is indeed another elimination of the tertiary alcohol. All right, so the if we have maybe secondary instead of tertiary, what we can do here. So maybe you have this one over here. Then what you can do instead is you can try to use the phosphoric chloride, and then you can do it with the pyridine. Okay. So what happens to this one is this is what it looks like. This is what it looks like. Okay, and then once again they try to bond to this one over here, okay? And this one will leave. So leave over here, okay? And then once they form that one, then they're going to actually also leave like this. Okay? So then you're going to have a positive charge on this carbon here, which is a carbocation, and then this hydrogen here will be actually picked up by pyridine here. Okay. And this will to this one. This goes to there. So this will be gone, okay? And now you have elimination over here. Okay. All right. So this is something you can do if you have a secondary or primary, because the E1 is optimal for the tertiary, very high degree alcohol. But this is something you can do instead. Does it make sense? Okay. It's pretty much the same, but it's just making a better leaving group. That's the key point. When it leaves, there's another either water or pyridine as like they behave like a base, so they pick up the protons there, so they can form like alkene compounds. Okay. But the main idea is pretty much the same, but different reason because of the how degree your alcohol compound is there. All right, then the next one. Here. So whenever you have a carboxylic acid here, you can treat it with alcohol, and you can make some ester compounds. Okay? So I will show you one thing here. If you have a benzoic acid here, and I'm going to treat it with the methanol with some acidic condition over here. And then what it does is And then what it does is because of the acidic conditions, they're also going to This one we're going to bound to the hydrogen cation. So they can be once again be better leaving groups with the positive charge. So that's why they're going to leave like this, okay? And then when they leave, it's positive charge. And if you look at this one here, they can be what? Methoxide and cation over here, bond together. Okay? So they will become this one. Okay? So as you can see, you can have some good carbonyl group, ether combined kind of acid group over here. Okay, so this is something also we can do with alcohol, with the carboxylic acid, so we can form some ester group here. There's another way, is the, once again, if you treat with the thionic chloride, you can actually see that this will replace by what? Much better leaving group, but at this time not water, but chlorine, because this is the chlorine. And then you can treat it with the methanol again. I'm just gonna write that. And then this will also, this is pretty good leaving groups, right, already. So this will make ester group here. So it's pretty much the same thing, but in a different pathway. Okay, but you can actually use the carboxylic acid compounds with alcohol. You can make some ester compounds. Okay, maybe can you guys try this one? Okay, so maybe we can show you. Try to do it with the okay. Maybe can you try this 1 or 2 minutes? We'll do this together. So carboxylic groups, alcohol can make ester group at certain conditions. Okay, that's the key. Okay, maybe 1 minute, we'll do this together. So carboxyl group parts with alcohol can become about 30 seconds. Okay, so this one will become what? This, okay. Do you see this, right? Okay, perfect. So once again, acidic condition, they can become water, and they leave, and now the methoxide will attack here, so they become O here. So you just put it there. Does it make sense? Can I move on? Oh, perfect. Alrighty. Okay, so the next one I think is So here's some compound. This is what we're gonna do is oxidation. So this is the geranium. What we're gonna use is the Dastmalchian per iodine name here. So if you have this type of compounds, you can actually make the aldehyde groups over here. So oh, I don't have a space. Just yeah, I'll just make it very small. Yeah, 1, 2, 1. Here, so this part here will become aldehyde. Aldehyde. So you see these aldehyde groups over here. So the but if you have oh, because this is this is what this is. So whenever you have the primary the alcohol, you can have the aldehyde. If you have maybe this one, okay, going with the same same thing, this one, this will become ketone. So this is a really good oxidation. Not just the hydrox group over here with this the carbonyl groups that makes this one aldehyde or even ketone. That makes much stronger bond between carbon and oxygen that makes more oxidizing the part of this compound. So this is the another one we can do this compound. Let me see. So. You guys maybe try this one. I'll give you this one. I'll give you about 1 or 2 minutes. And see, you can can you guys predict the products? Okay, about 1 minute. Seconds. Okay, so the trick is actually pretty simple. You just need to find where you have hydrox group, remove the hydrogen, and just double. So it makes your ketone. That's it. Okay, so yeah, I'll move. Can I move on? It just okay. So if it's primary, make sure where you have a hydrox group will be aldehyde. If it's the secondary, you have a ketone with this the Dexmartin pyridine is made. Okay. So the next one. Okay, so next one is let's try this one. Okay, so next one is this is what we call the isopropyl benzene. We actually call this cumene. This is cumene compound. And then you can treat it with some oxygens with a lot of heat. Okay. And then they can become cumene hydroperoxide. Looks like this. Okay, looks like this. Okay, and then you can treat it with a lot of the protons over there. What happened to this one here is this one will grab one of the proton here, so it becomes water on this part. I mean, this is the peroxide state, but here positive charge, and then when it goes, so this one wants to leave now. So then once it leaves, this becomes positive, right? So in that time, it shipped to the so okay, this carbon here. So when it leaves, this one now wants to ship to here. So in that way, if you look at this one, that way you can actually have this will leave, okay, as water. This one. So if you ship this Fanny group to the oxygen when it leaves, you can actually put the positive charge not here but the carbon, which is better because you don't want this positive charge on the oxygen, which is highly electronegative. So this is why leaving like this one. Okay, so this will become water, right? And then water actually comes to here because it's a positive charge. Okay, and then this goes to there. Okay, and then what happens to this one here is now once they become negative charge, it can grab the hydrogen cation and become phenol. Okay, so we can, and then this part later it bond to. So this is broken, right? In this way. Okay. So there's another water can grab this one. So this one goes to here. Okay. So it become two separate compounds can be with making phenol. So acetone and the phenol. Okay. So the this is a kind of a long process, but this is another way we can make some alcohol from the isopropyl benzene, or you can say cumene. So, yeah. So this is also another type of reaction we can do, making some alcohol. Okay. So I'll just stop here today. Okay. We're almost done with the